These are drilling-induced tensile fractures in wells off the Norwegian margin. They're absolutely clear in the image logs. And when we make a map of them, this is some work that a former student, David Whippert, and I did about a decade ago. There are image logs available from a depth of about 2,500 meters all the way down over 5,000 meters. There are 5 wells scattered about this fault that you see there. The colored image is the reflectivity of the top of the Brent Reservoir. These 5 wells have as many as, let's see, there's 90, 220, 618 drilling-induced tensile fractures. And in aggregate, we see that the direction of SH max is about 100 degrees north, 100 east, with a standard deviation of about 10 degrees. The stress is very uniform over this entire region. We're actually going to try to study the potential for slip along this fault. In fact, the cover image on my book is a perspective view of that fault, and we're going to resolve the stresses. We're going to ask, has that fault slipped, and if so, why? And we're going to use in that analysis the fact that the stress field is very uniform, and you can see that while in aggregate the stress is north 100 east plus or minus 10 in each of the wells, north 101 plus or minus 10, north 107 plus or minus 11, 97 plus or minus 11, 102 plus or minus 10, and so on. A very uniform stress field spatially and over a range of depths that really captures the fault. And when we start working on this question of is this fault going to slip or not, we pretty much have a pretty good handle on the stresses in this case. Here's the Timor Sea, some work by David Castillo, another former PhD student in my group. And what you can see here is that the stresses are kind of rotating in a unpredictable but systematic way. So for example, you can see the stresses here kind of rotating in that direction, and then in fact there as well. And then suddenly they're more northerly here. And so, one could attempt to build a model of the Earth and explain this in terms of the convergence between the plates in the region or some other process. And while, that's not the point of what I'm talking about now, the stress isn't perfectly uniform at the regional scale, but it's quite uniform, at the local scale. And so, depending on what your interest is, you work with that degree of variability or that degree of uniformity. And this is a case in California, the Elk Hills field. These are 3 anticlines in the western side of the Central Valley. These anticlines are currently growing over blind thrusts, reverse faults, that do not appear at the Earth's surface. And these anticlines are growing over those. It's an area, there are many naturally occurring earthquakes in the area, these active faulting, active folding, and yet the stress state seems kind of complicated, and it is complicated for obvious reasons. But again, if you were to say, just look at this, this particular structure here, what you would see is a very uniform, rotation of stress from being almost north-south to about north 45 east, as you go along, from one side of that anticlinal structure to another. Now, can you model that? Can you predict that? Maybe not, but you can map it. And once you've mapped it, for example, that if you were, I don't know, just to use an arbitrary example, if you were carrying out a hydraulic fracturing operation on this side of the reservoir, the hydraulic fracture would propagate more or less north-south, and over here it would propagate about north 45 east. Okay, so while this might have been too complicated prior to any drilling to get these details, once you've got the drilling, you've got some data, you can then work with that in a predictive way. Now, as we'll start in chapter, I'll mention it in chapter 1, but we really dig in chapter 6. We have a variety of techniques for stress orientation, a variety of techniques for relative stress magnitude, and a variety of techniques for absolute stress magnitude. And we'll introduce those through the middle part of the book. And why do we use these techniques? Because we're using data that comes directly from the reservoirs of interest. Okay? And with every well that is drilled subsequent to building the model, we get to test the model. Because once you know the forces, you can predict how wells are going to respond. So for example, suppose you have a few vertical wells in an area. You build a model. Okay, you have some degree of confidence in that model. But now you come along and you're going to drill a well with a more complicated trajectory. If your model is correct, you should be able to predict exactly how the wellbore failures are going to appear in that more complicated well. And if they do, it confirms your model. And if your model is incorrect, you've got to go back to the beginning and figure out what's going on. Is it spatial variations? Have I done something wrong? And so on. So these techniques we're going to use are testable. They're local. We work within a set of general principles, which I've introduced briefly and will build on more in subsequent lectures. We work in the context of these general principles, and then we build a model, and then we never stop testing the model, all for the same place. And that's why when you come to the application part of it, you have sort of an intuitive sense for how much confidence you have in your predictions, because you have a comparable intuitive sense for how much confidence you have in the model that's making those predictions. And so these techniques have proven to be very successful because it's not just a number that comes out of an algorithm. We're not just taking geophysical logs and putting it into some black box, and that black box is spitting out 3 principal stresses and an orientation in some mysterious way. This actually does happen, by the way, out in the real world. And it's highly unsatisfactory because you don't really know where those stresses come from. You don't know how much confidence to have in them. You don't know when you see something different, how to really interrogate, revisit, and improve the model, all of which you want to do. So these models are drawing upon lots of kinds of information, right? We're integrating information about the density to get the vertical stress. We're going to use hydraulic fracturing to get the least principal stress. We're going to use some information about wellbore failures to tell us about stress orientation and to put some bounds on stress magnitude, etc. Okay, it's an issue of integration and synthesis, and we never have data that's as good as we would like. And that's another thing you get as more drilling is occurring and more data is being obtained, is you get this ability to fill in the gaps in your model as well. I've been talking mostly about vertical wells. The principles are easy to understand. When you do the homework assignments, you will initially be working with vertical wells. But all of the principles apply to deviated wells, and the mathematics becomes more complicated because suddenly the reference frame for the wellbore is not the same as the reference frame for the stress in the earth. But nonetheless, we kind of go through it, and we walk you through it, and we'll show you exactly how to apply these principles. And it turns out that when you're looking at wellbore failures in deviated wells, you actually learn more about the stress field than you do from a vertical well. It's kind of subtle, but we'll illustrate that when we get to Chapter 8. And then finally, we'll do this kind of brief world tour in Chapter 9. I started working with Mary Lou Zobak in the late 1970s to demonstrate that we can build coherent stress maps. We started in the central and eastern United States. We went on to North America. And then in the late 1980s, she led an effort to build a world stress map. And this is a generalized version of that stress map. This is a database that is in the public domain. And in some places, there's actually pretty good data. And you can actually go to this website and learn at least at least about stress orientation and relative stress magnitude. It's a starting place. In many other places, the data are very sparse and incomplete, and so it's sort of a first clue, and then you kind of dig in and do the kinds of work we'll be describing in a minute. But it's really important to understand that as you go from place to place around the world, because geologic processes are different, the stress state's different, the pore pressure is different, the rocks are different. And so that's why we start from these sort of fundamental principles rather than just sort of introduce you to some general correlations, for example, between stress and depth that might be applicable in one place but completely inapplicable in others. I've mentioned critically stressed faults and fluid flow. In terms of applications, there's been one just beautiful case study published in the AAPG Bulletin on critically stressed faults and flow in a gas field in Southeast Asia. This is work by Peter Hennings and others. Basically, these are wells drilled into a fault in crystalline rock and in some very impermeable rocks near the nose of the anticlinal structure. And what they found is they couldn't predict why wells would be good wells or bad wells. It was kind of like shooting in the dark. So they basically went through a process of building a geomechanical model, as you will do in the data we give you in this class through the exercise. From that geomechanical model, they figured out which faults were critically stressed. They correlated the critically stressed faults that they had in the wells with the well production and saw a very good correlation. They completely changed their drilling strategy so that they were drilling wells through the damage zones associated with secondary faults. And when they did, they saw a very strong correlation between the well performance and the number of critically stressed faults that were encountered. In other words, by optimizing the intersection with active faults, which are hydraulically conductive, they maximized the productivity. And these wells are killers. The number here, 1, is 1 BCF per day of production. Now, if you might give that some thought, to put it in reference, a shale gas well in the Barnett Shale in Texas will produce something between 2 BCF and 4 BCF over its lifetime. Okay, that's 1 BCF per day by intersecting several hundred critically stressed faults in this one particular well. In fact, they can't produce the well that fast. They have to choke it back because the flow rates would sort of destroy all the surface equipment. But it's a published study in AAPG. We'll go through it in more detail in Chapter 11. And finally, compaction and subsidence are two sides of the same coin, obviously. Weak sediments, large pore pressure change, you get compaction. Compaction can be bad. It can damage wells. Compaction can be good. In a case in the Gulf of Mexico, which we'll study in some detail, you can actually demonstrate that the compaction drive through this is actually a term paper topic from a previous year. A student built a very simple compaction drive model. And when he did, he showed that taking a compaction drive into account, one would predict far greater recovery than if we were just considering the reservoir to be elastic and depleting. Now, this is a good idea to a point, right? You can't, compaction drive then can be a great way of getting the oil out of the reservoir, like squeezing the water out of a sponge. But if there's too much compaction, you'll be destroying your wells. And if there's too much compaction, depending on the thickness of the reservoir and the depth, you can get subsidence. And one place we've been studying subsidence is in coastal Louisiana. That fellow's no longer, his house is gone, and he's not very happy about rising water. The rising water has been associated with the abundant oil and gas production in coastal Louisiana. That's the red areas shown on the left. The growth faults in the area are the yellow lines. And it has been hypothesized that the compaction of the reservoirs at depth has caused surface subsidence and very significant coastal erosion and land loss. We've studied that process in some depth. We've used leveling data, which is data collected along these green dotted profiles across several fields. We've studied it analytically, and we'll use a model developed by Geertsma to look at surface subsidence in response to compaction. It's a relatively simple analytical model, but gives us a good idea of what goes on at depth. And we compare our theoretical calculations with the observations across these oil fields. And what we can demonstrate is there's a little bit of subsidence at the surface due to the compaction of those fields. And we'll work all the way through that. It's just a couple of centimeters of compaction. But the big issue actually causing the coastal erosion and the land loss in this part of the world is the fact that the Mississippi River has been channelized, and you don't get the normal flood process restoring sedimentation along the coast that offsets the steady state subsidence due to compaction, which has been occurring over millions of years. We'll go through that in Chapter 12.